Okay, then good evening to all of you, and welcome back to the problem solving session of the Introduction to Fluid Mechanics course, and we are in the week 9 of this course. So, in this week's session, we will be primarily dealing with one of the very important topics, or as I can say, is one of the cornerstones of the subject of fluid mechanics, and which plays a vital role in understanding the modification in the governing equations that are being made to make them suitable for the analysis of fluid mechanics problems. Okay, so we initially discussed about two different approaches of solving fluid mechanics problems, that is the Lagrangian and the Eulerian approach. We also saw their pros and cons, like how the Lagrangian approach, like even if it is very highly accurate, but comes with its own problems of having a very high computational cost or very high uh, cost in general. Like even if it's not computational, even if it is done with hand, it just has a needs lot of efforts and time to reach into a proper conclusion for the given problem. But again, we also discussed about a different alternative, that is the Eulerian approach, of how that approach, even if comes with certain approximations that may sometimes lead to a certain degree of inaccuracy in the results, but it can help to deal with simple fluid mechanics problems, and most importantly give us a very uh, I must say accurate insight to the problem in hand, of how the flow parameters or the flow properties may change with time or space, given we know the inlet and exit velocity profiles or the flow properties. Okay, so that's how we came into we discussed about the two existing uh, uh, methods of solving fluid mechanics problems. So the Reynolds transport theorem, and so again, while as we know that most of the laws that primarily govern the subject of fluid mechanics, say it the conservation of mass, conservation of momentum, or conservation of energy, so these laws were something that were that were discovered or derived for a control system, that is an entity having a fixed mass and a fixed identity, right? And and these are laws of classical mechanics, and thus they are derived or made with respect to a particular mass of having a fixed identity, that the identity of the mass also does not change. Okay, but as we saw that, and we can correlate this system approach to the Lagrangian approach in some sense. Okay, but we saw that for especially for fluid mechanics, this Lagrangian approach of solving the problems come with its own issues or its own consequences, right? So to deal with such kind of issues, we derived a control volume approach, and it is here itself where the concept of Reynolds transport theorem comes into picture, because since the equations of classical mechanics that govern the conservation of mass or conservation of momentum were written for a control system, and we saw that since this control system approach is not that suitable for solving day-to-day life fluid mechanics problems, so we needed a tool or method to transform these initial governing equations that were made for a control system. We needed a transformation that could transform or modify these equations for our control volume analysis, and that's where the Reynolds transport theorem comes into picture. Okay, so in simple words, the Reynolds transport theorem is just a mathematical transformation that could change the governing equations of a control system to a control volume approach. Okay, and thus the name uh, Reynolds transport theorem. Okay, so again, as per the regular agenda of our problem solving sessions, I will not go through the detailed derivation of Reynolds transport theorem or RTT that I will say from now onwards, because if any one of you would have attended the lecture by Professor Chakraborty, you would see that Professor Chakraborty has given ample amount of time or ample amount of discussions that could make you understand the very concept or very origin of this Reynolds transport theorem by detailed derivation. So I would suggest that you go through that derivation once again if you have any doubt regarding the origin of this Reynolds transport theorem, right? So I will just go through the governing equation that is or the transformation that exists. So in the case of the Reynolds transport theorem, so there are two different approaches that are involved in the same equation. Okay, so there is a control system approach and a control volume approach. Okay, so so the Reynolds transport theorem basically says that the rate of change of a particular extensive property n is actually equal to the local rate of change of the property for a particular control volume plus the net efflux of the particular property from that particular control volume. Okay, so this term, this control surface integral gives us the net efflux out of the chosen control volume. Okay, so in this equation, this capital N denotes the extensive property that we are going to conserve, say mass, momentum or energy. Okay, and the term small n denotes the respective intensive property of n. Okay, if it is energy, then small n would be energy per unit mass. If it is momentum, then it would be momentum per unit mass. Okay, so basically it is small n is equal to capital N by m. Okay, so and in the second term, like sometimes students get confused with this term CS. They assume that it is a control system, but it's actually not, because all the terms on the right hand side of this equation are for control volume, and on the left, for the left hand side, it is for a control system. Okay, we are just trying to relate the rate of change of the property in a control system for a respective in terms of a respective control volume. Okay, so this CS actually denotes the control surface surrounding the given control volume. Okay, and here VR actually denotes the relative velocity of the fluid that comes out of the of the concerned control volume with respect to the velocity of the control volume itself. So if the control volume is stationary, then VR would be equal to the velocity of the fluid itself. Okay, and if the control volume is moving in the direction of the efflux of the fluid, then we need to consider the relative velocity of the fluid with respect to the control volume. Okay, if the control volume is moving. Okay, and n cap denotes the normal vector with respect to the area through which the fluid flows out. Okay, flows out or flows in. I hope that's clear. So this equation is very important. There's a general canonical form of the Reynolds transport theorem or RTT that we are going to use for mass conservation, linear momentum conservation, angular momentum conservation, and energy as well. Okay, but for this week's session, we are now primarily concerned with the application of Reynolds transport theorem for the conservation of mass. Okay, and this week's session is going to be quite limited, because it's quite small, because we are only trying to discuss the conservation of mass as per the syllabus for this week's session. But it's again very important, because even though if it's very simple, it acts as a stepping stone for a beginner or a person who is trying to understand or learn the concept of RTT and its application. So the conservation of mass acts as a stepping stone for the particular learner to understand this, how to apply RTT for a particular fluid flow problem, and then just use it for different conservation laws, say for momentum conservation or energy conservation. But the very concept of applicability of the RTT could be very well understood by starting with problems that deal with the conservation of mass. Okay, so for the conservation of mass, we'll directly consider the canonical form of the Reynolds transport theorem, and in that we will substitute capital N with m, that is the mass of the fluid that is under consideration, and small n will just become capital mass by mass, so the small n will be equal to 1. Okay, so just substitute capital N is equal to m and n is equal to 1 in this equation to get dm by dt for the control system is equal to dou by dou t of the control volume integral of rho dv plus the surface integral of rho vr dot n cap dA. Okay, and from the conservation of mass we know that the mass within a system can neither be created nor destroyed. That is basically that the mass within the system remains constant, because we saw that for a control system approach, the mass and the identity of the mass remains constant. So this term on the left hand side will be equal to 0, and we are only left with the right hand side term equated to 0. Okay, so that's basically the conservation of mass, or the canonical form of the conservation of mass that we will use for our different fluid flow problems, and we will see how we can simplify these integrals accordingly by taking the concerned assumptions for a particular problem. Okay, and since it is the most generalized form of mass conservation, so the control volume that we choose can be moving as well as deformable. Okay, so there is no assumption applied here yet. Okay, so it's a very generic form. So the control volume that we are going to analyze with this form can be moving as well as deformable. Okay, so there is no specifications or simplification applied. So if at all necessary, we will see how a particular application of a certain assumption modifies this form of the governing equation for the conservation of mass. Okay, so let us discuss a particular problem that again deals with conservation of mass, and this problem was again discussed by Professor Chakraborty in the lectures. So my practice is to revisit the problems discussed by Professor Chakraborty, because the problems discussed by Professor Chakraborty himself are in itself are very self-contained and enough for a beginner to understand the concept in a very beautiful, very in a very satisfied manner. So that's why I prefer to repeat the problems taught by Professor Chakraborty, because I myself get to learn a lot from his insights on the problems. Okay, so since we are going to discuss some problems in this session that will again help you to solve the question that is being asked in this week's assignment. So in order to help you approach the problems that we are going to discuss today, a revision of the problems taken by Professor Chakraborty in the lectures, I feel that is a very good practice. Okay, so the question is that air is being pumped in a balloon. Okay, so the direction of air is being shown here. So the air is being pumped inside the balloon, and the volume of the balloon changes with respect to time. Okay, so we are asked to find the rate of change of volume of the balloon with respect to time. Okay, we are asked to find dV by dt. Okay, so now here you can clearly see that a logical approach, or a logical understanding of the problem will tell you that it's the primary concern that we have in this particular problem is the rate of change of mass, or mass related issues that comes into picture, that are the mass related issues of this particular problem becomes our primary concern. So a logical approach to this problem will tell you that a mass conservation analysis of this particular problem will give a proper insight, or a correct insight of the given problem. So we start with the application of mass conservation for this particular problem. So again, it may happen that for a particular problem, we may again deal with a scenario where we are asked to find the net force or net drag acting on a particular, say, a particular airfoil or flat plate. Okay, and in those kind of problems, you can clearly see, since it deals with a net force that acts on the body, so force is basically the rate of change of linear momentum. So we can say that a linear momentum conservation analysis would give us a proper insight to the particular problem, or how it uh, or how the various parameters changes in the flow. So a linear momentum conservation would give us a proper analysis in the case of problems that have that deal with the finding of force or net drag that act upon the body. Okay, so that's a logical way or logical method to understand which conservation law to apply in a particular problem. Okay, so I know obviously that it's a very trivial thing, but still, as a tutor or as a TA to this problem solving session, I preferred to discuss this with all of you, so that you can understand of why a particular conservation law is applied in a given problem. It's just a logical approach, a logical understanding or analysis of the problem in hand. Okay, because often at times I say say the students that attend this session that for fluid mechanics is a very it's a highly mathematical heavy subject. Okay, so there are derivations, there are equations, there are various steps involved even in any kind of problem. Okay, so I suggest them that, if you are very well versed with these three conservation laws, that is the conservation of mass, conservation of momentum, and conservation of energy, and if you are even if you don't understand how to solve the problem in the correct way, if you don't know the correct way to solve the problems, a insight or a application of these three conservation laws, or how you're able to approach the given problem in hand by using these three conservation laws, I feel like will be enough for you to even get half marks or even 60% of the marks for a given problem. Why? Because any examiner that is going to analyze your your paper will see that the student has an idea that for any fluid flow problem, these conservation laws have to be maintained, or at least have to be looked upon from the perspective of these conservation laws. Okay, so if you're well versed with these conservation laws or how they're applied for a particular problem, you will be able to handle any kind of problem, right? And you will eventually see that most of the problems that we're going to deal with from now onwards are just the application of one or the other conservation laws. Okay, for particular chosen control volume. Okay, so that's how I feel that it's a very good practice to be well versed with these three conservation laws, and to be properly and to properly remember these conservation laws or its generic form. The canonical form of the RTT helps a lot. Okay, it's just the changing of the capital and the small n in the equation. So that's why this week session, I feel, even though it may not be that long, but it's very important, because it gives you a very good insight of how to approach the problems and how the canonical form of this RTT is useful to understand these three fundamental conservation laws. Okay, so for the given problem in hand, by applying the conservation of mass, so first of all we need to choose the control volume. Okay, so the control volume that we choose is the surface just outside the surface of the balloon. So we choose that, and again the choice of control volume can also be very it can vary from person to person. Okay, so a person can view a problem in a different way, so he or she can choose their particular choice of control volume. Okay, but still, as you will see in the next problems or the following problems, that a proper choice of control volume also simplifies the problem a lot. So a clever choice of control volume is also a very important thing to know while approaching these fluid mechanics problems. Okay, so for this case, now we will choose this red dotted line as our control volume, and if we have that apply conservation of mass, we will get that dou by dou t of integral of rho dv, because of volume integral of rho dv, volume integral of rho plus 0 minus m dot in is equal to 0. Okay, and you will understand, you will ask why it is 0, because since you can clearly see here is that, so this term, if I zoom out a bit, yes, so this term can basically be, is basically the net mass flux out of the control volume. Okay, so basically m dot out minus m dot in, and since m dot out is 0 for this particular case, because all the air being pumped is being stored within the balloon itself, that in fact inflates the balloon to a larger volume. So m dot out is equal to 0, and that's why we have this term, this 0 in this conservation law. So we have that. Now we can try to see how we can simplify this equation even further. Okay, so now if we take an assumption that rho is density is not a function of time, okay, it's uniform or constant, then we can take this density out of the integral as well as the time derivative. Okay, but again, this assumption that density is uniform and independent of time, it's a very, very bad assumption, actually very bad assumption. So we are saying it's a very crude assumption, like we are taking the most simplest possible model or most simplest possible way of handling this problem. So whenever you're going to apply this such kind of crude assumptions, it's better to mention it in the solution itself, so that examiner knows that where you are going wrong. But he will give you marks because you have your method is correct to solve the problem, but he will at least know that you yourself know that the approach that you have chosen or the assumption that you have chosen is completely, or I'm not say completely, but very, very wrong. Okay, and about this, I guess Professor Chakraborty has discussed in the class that why it is wrong, because since air is being pumped in a particular confinement, in a balloon, so it is bound to have a variation in the density of, it is bound to have a certain variation in its density with respect to time. Okay, because air is pumped in a particular confinement, and it is a different air pressure within that itself results in that itself supports the inflation of the balloon. That's why certainly there is a change in the density of the air. But you're saying that let us take a very simple assumption. Let us take that density is uniform and independent of time, so that we can take out this density out of the integral as well as the derivative. Okay, because we need the derivative of volume with respect to time. Okay, we need that term. Okay, so just 1 minute. Okay, so once you take that crude assumption, so let me just write it, very crude assumption. Oh, I'm sorry. Okay, sorry. So I'm sorry, my screen got disconnected. So just a second. Okay, so I'm sorry, so my screen got disconnected for a while. Okay, so once this assumption is applied, that is rho is uniform and rho is independent of time, so we can take the density out of the time derivative as well as the volume integral. So once we do that, we can write rho dv cv by dt is equal to m dot in. Okay, and since we know now want this term, so we can just take rho in the denominator, so we can write d vcv by dt is equal to m dot in by rho. Okay, so I guess that's the problem here, so that's fine. Now, okay. So now let's us, as I told, that if we take certain assumptions in the for the generic form of the generic form of the conservation of mass, we can simplify the equation this form of the RTT or this form of the mass conservation even further. Okay, let us see how. So now if we take two assumptions, the first being a non-deformable control volume, so that will help us to take, or that will allow us to take the time derivative within the volume integral. Okay, so if we consider a non-deformable control volume, then we can take the time derivative within the volume integral. Okay, and now if we consider a stationary control volume, okay, then as I mentioned, this VR is actually the density of the fluid with respect to the control volume. So if the control volume itself is moving, because there is no restriction in the initial derivation of RTT that the control volume has to be stationary. So no, it can be moving, but that's why it is VR. Instead of V, it is VR, which mentions that VR is the relative velocity of the fluid coming out of the control volume or a particular phase of the control volume with respect to the velocity of the control volume itself. So now if the control volume is stationary, then the relative velocity would be equal to the velocity of fluid itself, right? So once you do that, once you put in these two assumptions, that non-deformable control volume, so the time derivative comes inside the volume integral, and a stationary control volume, so that VR is equal to V, that is the velocity of the fluid. Then by applying the Gauss divergence theorem in this term, we can convert this surface integral to a volume integral. And once we do that, we can club together all these terms, because they both are a volume integral over the same control volume. So we can write the volume integral of dou rho by dt plus the divergence of rho v over a particular control volume is equal to 0. And given that this choice of the control volume is or this elemental volume is arbitrary, over which we do the volume integral, then we can write the only way that this integral is 0 is that if the integrand of this integral is equal to 0, right? That is dou rho by dou t plus the divergence of rho v is equal to 0. Okay, and this is the conservation mass conservation in the differential form. Okay, so now let us take a second example, a second question, a second problem. So consider this particular diagram. Okay, so here it is mentioned that there are two hands or two arms for this particular vessel, where at the inlet the velocity profile is uniform. So if I zoom it a bit, so the velocity profile is uniform at the inlet, so it is defined by u infinity, it is constant, and in the exit the velocity profile is defined by u1 is equal to u naught 1 minus y1 square by h square. Okay, so density is constant according to the question, so we are asked to find u naught. Okay, so in this given problem, if we consider that the density and the volume of the chosen control volume does not vary with time, okay, then we can completely disregard the first term, that is dou by dou t of the volume integral of rho dv, right? Because since the density and the volume is constant with respect to time, then the derivative will be equal to 0. That's why we are only left with the second term, that is the net mass flux out of the control volume. So what it says is that the net flux out of the control volume is constant. Okay, so what it basically says is that the net mass flux from the inlet arm is equal to net mass flux out of this outlet arm. Okay, so you can say or outlet. So for the inlet that has an area of a naught, we can write the net since density is constant, we can, rather than instead of choosing the mass flux, we can deal with the volume fluid as well. Okay, so if density is equal to constant, then we will have that q1 is equal to q2, or q inlet is equal to q outlet. Okay, if density is equal to constant. So if we say that, then for the area at the inlet, then the net volume flow rate would be given by minus u infinity h by 2 into b. Okay, why minus? Because the direction of the velocity profile or direction of the net velocity is against the direction of the normal vector of the particular area. Okay, and that's why the negative sign. And for the area A1, we would have an integration from, we can find the net volume flow rate by taking the integration of this over a particular area, right? So once you do that, we'll have that the net volume flow rate will be equal to integration of u0 1 minus y1 square by h square dy1 into b from minus h by 2 to h by 2. Okay, so if this is the total height or total width of the arm, then we can take the integral from minus h by 2 to h by 2, right? Because the coordinate system that we have chosen, that is y1 x1 coordinate system, that it has the origin at the center line. Okay, and that's why the integration varies from minus h by 2 to h by 2. Okay, and once you do that, again I have not solved it, so the net volume flow will be equal to the sum of these two terms. So once you do that, we'll have that this integral would be equal to u infinity h by 2 into b. And once you evaluate this integral, you can correlate, you can represent u0 in terms of u infinity and the known parameters, that is h and b. Okay, so I hope this integration is very simple, so I just left it. You can go ahead and try to solve it. Okay, so let us look into the next problem. So before that, I would just like to give you 2 minutes to digest or analyze and understand the concept that we have discussed till now, because this is the final problem I guess we will be dealing for this discussion part, and then you can directly go to the problem solving part, right? So this is the last problem that we are going to discuss, that has an application of mass conservation, and then we can directly go to the problems in our problems for this week's problem solving session. But before that, I would just like to give you 2 minutes to discuss or recapitulate the things that we discussed till now, that is related to mass conservation and RTT, so that we can approach the problems for this week for this session in a very appropriate, or in a very in a much better way. Okay, so I will give you 2 minutes for that. So okay, so sorry for the delay. Now I guess we had enough time to revisit or rethink the topic that we've discussed today, so that's fine. Now we can directly deal with the final question for the discussion part of this today's session. So let me zoom out a bit. Okay, so now we have a similar geometry in our hand like the previous one, but in the previous case we had that the height of the fluid within the control volume or the container was constant, but in this case the height of the fluid changes, which again results in a deformity of our control volume. That is basically the volume of our chosen control volume changes with respect to time. So the first term that we have in our hand, even if the density is constant, but since the volume of the control volume itself changes, so that will have a non-zero value. Okay, so the first term, that is the time derivative part, will be non-zero in this case, and will obviously have the net volume flow rate or the mass flux terms. Okay, so similar geometry, same, there is an inlet velocity and so there is an incoming volume flow rate from both the sides of the both the sides of the arms of the vessel, and the height of this fluid is changing, and as per it seems it would increase with respect to time because fluid is being injected from both the sides, right? So density, they've given the density is constant, you need to find the variation of height with respect to time for this particular control volume or particular vessel. Okay, so so let the first choice of our control volume be the red dotted line that varies from the inlet of the two arms, it cuts the inlet of the two arms, and then the upper edge or rim of the container. Okay, so we'll see why not the blue one. Okay, that's also a choice of control volume. It depends on on the choice of a particular student or person who is trying to solve the problem. So just completely independent choice. There's no particular hard and fast law for choosing control volume, but we'll see why this particular choice of control volume can help us to simplify the problem a lot. So they mentioned that there's a uniform velocity profile at the inlet, at both the inlets. It's V1 and V2, they are uniform. So basically the velocity profile at these two inlets are known. Okay, so from mass conservation we can write dou by dou t of the volume integral of rho over CV plus the net mass flux coming out of the control volume would be equal to 0. Okay, and now since the density of the density of the fluid is constant within the control volume, so we can write it as, so if density comes out, it will be just dou by dou t of CV CV into dV, right? I just write it so that for reference. So if we do that, then it is rho volume integral of basically the volume, it is basically the volume of the instantaneous volume of the fluid within the container. So since it is not completely cylindrical, and we don't know, they have not mentioned the surface of the radius of the or even the dimension of the container in our hand. So what we can ideally do is that the net volume of the fluid in this vessel could be equal to A into H. Okay, it's a very crude assumption again because we are not taking into account the volume of fluids within these arms, but as I already mentioned, the very concept of Eulerian approach of solving fluid mechanics problems is to compromise the accuracy but help we tend to get the proper insight of the problems by compromising the accuracy but simplifying our calculations. So we can analyze more kinds of problems in a very faster manner by compromising the accuracy. But again, we saw that the very experimental analysis or analytical analysis tells us that the degree of accuracy of the results is quite acceptable even by, while compared to Lagrangian approach, but sometimes accuracy, when accuracy becomes important, the Lagrangian perspective of solving fluid mechanics problems comes into use, right? But since we are dealing in a very basic fundamental level course, where the fundamental objective or basic objective of the course is to teach students to understand fluid mechanics and apply the well stated laws or methods to solve fluid mechanics problems. So a certain lack of accuracy in the cost of understanding the problem in a much better way is acceptable. So if we just assume disregard the volume of fluid within this arms, say we can again take an assumption that the volume of the fluid within the arm is much less compared to the volume of fluid within this section, then we can write the net volume of the fluid is equal to A into H. Okay, this area of the container, if it is cylindrical, they have not mentioned it, into the height of the fluid within the container, okay, the instantaneous height. So we can write this as rho d by dt, into H. Okay. Now you may ask why we have changed the partial derivative to a complete derivative, because the area remains constant, right? The area of the fluid in this part remains constant, in this container remains constant. So the only parameter that is changing is height, and height is only changing with respect to time. Okay, and we have mentioned that height is only a function of time, and that's why you can change or convert this partial derivative to a time derivative. Okay, partial derivative into a complete derivative. Okay, this is again a very popular law or rule through which this transformation can be done. That is, there is a Leibniz rule. So we can go and look into that as well to come to the conclusion. But it's a very logical way or simple way to transform this partial derivative to a complete derivative. Okay, but again, it's a good practice to look into the this law that governs these transformations. That is known as the Leibniz rule. Okay. So once we do that, so we will have that again A is independent of time, then rho A dH by dt minus rho A1 V1 minus rho A2 V2 is equal to 0. Why this minus sign? Because in both the cases fluid is being pumped inside the container, which results in the direction or the direction of the velocity to be in the opposite direction of the area normal vector of the particular inlet. So that's why it will be negative for both the cases. Basically both acts as inlet in this case. So we would have rho A dH by dt minus rho A1 V1 minus rho A2 V2 is equal to 0. So if we simplify these terms once again, we can write dH by dt is equal to 1 by A A1 V1 plus A2 V2. Okay, so this is the approximation of the rate of change of height for this particular control volume. Okay, so the next query was that okay, now you have chosen this to be your control volume, but you again compromise the accuracy by disregarding the volume of fluid in these arms. Okay, which in some cases, if the arms are too large, is a very high loss in the accuracy, in the high degree of loss in the accuracy of the problem. Okay, but so you may suggest that let us not choose the red dotted line as the control volume, since we know the actual volume of the fluid in this part. Let the blue dotted line be the our chosen control volume. Okay, that's again completely fine. It's nothing wrong in choosing this blue dotted line as your control volume, but the issue lies in the fact that no one knows the velocity profile in these particular regions, in these two parts. Okay, because we are told in the problem itself that the velocity profile is uniform in these two inlets. So but there is no information regarding the velocity profile of the fluid in these regions. Okay, so and this uniform profiles being uniform is again a very good approximation, because since the fluid is being injected at that part, then then the fluid can be essentially be considered to have a uniform velocity profile at the inlets, okay, not being affected by the walls. So you can just tell that the fluid is injected at this particular inlets. Okay, now this velocity profile at this place, this part can also be approximated. Okay, so if we consider this, say assume it to be cylindrical, and if we know the velocity profile at the inlet is uniform, again we can apply the conservation of mass to find the approximate velocity profile at this region. Okay, it is not I'm not saying it's not at all possible to find the solution. It's always possible, but again you need, it's a very tedious and time consuming work to find the velocity profile at the inlets. Again you need to apply the conservation of energy to take into account the height difference in these two regions. So it is possible, but it's a tedious job to find a velocity profile there, okay, in these parts. So to help us to avoid this calculation with a cost of a slight loss of accuracy in the problem, we just take control volume that helps us to choose the correct velocity profile in the cost of compromising accuracy by choosing a slightly approximated control volume, okay, or the volume of the fluid contained within the control volume. So that's the catch all in all. Okay, so you need to be very wise by choosing the control volumes, and a wise choice of control volume can itself help us to simplify the problem a lot, okay, which we'll eventually see in the next session, where we're dealing with conservation of linear momentum, where how the choice of control volume in fact allows us to even disregard the calculation of net mass flow rate from a particular phase. You will see that's a interesting example that we're going to discuss in the next week's session. So let us leave it for that. But a choice of control volume, as I'm saying from now itself, is a very helpful or a proper choice of control volume is a very important parameter, a very important factor in solving this kind of problems. Okay, so just to give a slight insight on what we're going to discuss next week, that is basically the conservation of linear momentum. So again we go back to the canonical form of the Reynolds transport theorem that is given by this equation. Okay, but in this case now, instead of n being equal to m, we take that n is equal to the linear momentum, that is mass times the velocity, which is a vector in this case. Okay, mass times the velocity. So we can substitute capital N is equal to mv, and small n would basically be equal to v, the velocity vector, right? So once you do that, and again we know that this rate of change of linear momentum for a control system is not equal to 0 in the case of conservation of mass, but instead is equal to the net force that acts on the control system. But again, in the limit of delta t tends to 0, this net force that acts on the control system will be equal to the net force that acts on the control volume that we have taken into our consideration. Okay, so once you do that, I'm sorry, just substitute capital N is equal to mv and small n is equal to v in this canonical form of the Reynolds transport theorem to get that dmv by dt, the system, control system, is equal to dou by dou t of the volume integral of rho v over the control volume plus the surface integral of rho v into vr dot n cap over the control surface, that will be equal to the net force that acts on the control volume. Okay, and the catch is that v in this case is the absolute velocity of the fluid, but this velocity within the within the brackets is actually the relative velocity of the fluid, okay, with respect to the control volume. So if the control volume is moving, okay, if the control volume is moving, then this v and this v will be different, okay, because this is the relative velocity and this is the absolute velocity of the fluid. This is very important to remember. Sometimes this very slight lack of understanding of the governing equation can lead to a very silly mistake in the exams. Okay, so in order to avoid that, just I'm trying to repeat it again. in the canonical form, we substitute small n as the absolute velocity of the fluid. Okay, but the canonical form, the RTD itself has a velocity embedded in the mass flux term, right? And that velocity that is embedded in the mass flux term is actually the relative velocity of the fluid with respect to the control volume. So if the control volume is stationary, that's completely fine. VR will be equal to V. That is the velocity of the fluid. This is the absolute velocity of the fluid. But if the control volume is moving now, so one of the velocities that is being conserved is the absolute velocity of the fluid. Okay, I'm sorry, I think I'm going fast. That is, this one of the quantities that is being conserved in the equation is the absolute velocity of the fluid, but other velocity that is embedded in the mass flux term is actually the relative velocity of the fluid with respect to the control volume. Okay, so I hope that is clear. I have emphasized it again and again because that's a very important concept. So I hope you don't forget it, but let's see, we will discuss it when we are going to discuss the problems related to conservation of linear momentum in next week's class. Okay, so I think now we can directly go and try to solve problems related to mass conservation and Reynolds-Sarsfield theorem for today's session. Okay, so we can start with the first question, and I will say this week's session questions are not that difficult, but again they're very important because they give us a very good insight, a proper insight of how to approach the problem from the perspective of Reynolds-Sarsfield theorem and consequently mass conservation. Okay, so I'll just give you 1 minute to go to the question. Meanwhile, just go to the question and see. Okay, just give me 1 minute. Meanwhile, you can go to the question. I'm sorry for the delay. So I was just engaged in some household works. I'm very sorry for the delay, but sorry. So let us just go to the question once. Okay, I hope you have already gone through it, but let us just try to revisit. Okay, so the first question is the velocity field in a region shown in the velocity field in the region shown is given by V is equal to AI cap plus BXJ cap, where A is equal to 10 meter per second and B is equal to 5 second inverse. Okay, for a 1 meter cross 1 meter triangular control volume with a depth of 1 meter perpendicular to our diagram, an elemental area 1 may be represented by dA1 is equal to W dy I cap minus W dx j cap, and the element of area 2 by dA2 is equal to minus W dx j cap. Okay, so they've already given the form of the area, okay, the elemental areas. Okay, these are key terms here. So the first question is, what is the expression for V dot dA1? Okay, and I think it's a very simple question. You just need to take the dot product of the given velocity field and the area vector. Okay, so once you do that, if I go to the solution, so once you do that, since V is equal to AI plus Bx j cap and dA1 is equal to W dy I cap minus W dx j cap, So we need to find V dot dA1. So once you do that, we will get that V dot dA1 would be equal to dot product of aik plus bx j cap with w dy I cap minus w dx j cap. So once you take the dot product, you will get a w dy minus bx w dx. Okay, and since we know a is equal to 10 and b is equal to 5, just substitute the numerical values to get that v dot dA1 is equal to 10 dy minus 5 x dx. Okay, so once you do that, you can see that the correct answer for the given problem would be option A. Okay, 10 dy minus 5 x dx. Okay, similarly for question number 2, we are asked to find what is v dot dA2. So just take the dot product of the given velocity field and the area vector dA2. So and once you do that, you will find that v dot dA2 would be equal to ai cap plus bx j cap dot product with minus w dx j cap. And once you do that, you will get that v dot dA2 is equal to minus bx w dx, that is equal to minus 5x dx. So the correct option would again be option number C. Okay. And the final question is, what is the expression for v times v dot dA2? Okay, so so we'll see that here v is a vector, but the dot product will give us a scalar. So this would basically be a scalar multiplied with the given velocity vector, which will again be a vector. Since we already know v dot a2 is minus 5x dx, so just multiply minus 5x dx with the velocity vector. So once you do that, you will get that ai cap plus bx j cap multiplied by minus 5x dx, that is equal to v dot a2. Let me just show it. You will get v times v dot dA2 would be equal to minus 50x dx minus 25x squared dx j cap. Okay, so the right option would be option number B. Okay, so it's quite simple, very simple, just multiplication or just an idea of vector products, dot products of vectors. So that's all. Okay, so let us go to the next question. So we have a cylinder in this particular problem. So you can go to the question for a while. Then I can discuss the question. Okay, just go to the question for a while so you can get an idea of what we are going to discuss. Okay, so I'm again sorry for the delay. So let us go to the questions. Okay, water fills a cylindrical tank to a depth of h. Okay, let me zoom out a bit. A tank has a diameter of d. Okay. Diameter of the tank is D. The water flows out an average at an average velocity of V naught from the hole at the bottom of area A naught. Okay, so the water flows out of this hole that has an area of A naught. Okay, find the expression for the instantaneous rate of change of depth dH by dt. Okay, so here again you can see that since the mass of the fluid is changing in this particular in this particular cylindrical tank, so you can see that a clear indication that we get from this given problem is that we are dealing with a rate of change of mass. Okay, and since the rate of change of mass comes into picture, you can say that a correct approach would be to apply the mass conservation for this particular problem. Okay, since there is no discussion about net force that acts on the tank because of the injection of the fluid out of the hole, so and they are only asking to find the rate of change of this depth, so a simple application of the mass conservation would give us the proper insight, or would even help us to solve help us to find the rate of change of height of the fluid in the container. Okay, so if you apply the conservation of mass for this particular tank, a particular problem, so we can choose the control volume to be of this form, because we know that the velocity profile at the exit of the hole is V0. Okay, and once you do that, we can write the mass conservation, the generic form of the mass conservation, that is dou by dou t of integral of rho dV plus the net mass flux is equal to 0. Okay, mass plus out of the control volume is 0. So if we take the density of the water be constant, because we are told that it is water that drains out of the tank, and moreover since it's only draining out, so it is very low velocity, so there is no factor of having compressible nature of the fluid in this case, that is water in this case, so we can essentially take the density of the water to be constant. Okay, so unless and otherwise mentioned, it is a good approximation to take the density of water to be constant. Okay, but you also look into the problem. Okay, if there is a compression involved, then obviously we need to take the compressibility effect, but other than that, since it is only draining, so the so the density of the water in this particular case can essentially be taken to be a constant. Okay, so if we take the density out of this equation, or density common from both these terms, we can take density out, so we are only left with these two terms. Okay, and the instantaneous volume of the control volume can be given by pi by 4 d squared h. Okay, where h is a function of time. Okay, because it is h that is the one that is only changing, diameter remains constant, right? So we will have d by dt of pi by 4 d square h plus a naught v naught is equal to 0, and if we just again rearrange the terms, we will get that dh by dt is equal to minus 4 a naught v naught by pi d square. Okay, and if we check the given options, so you can get that the correct option is option number D. Okay, so let us look into the next question. Okay, this is a very again interesting question. Why? We will eventually see. An incompressible fluid of density rho flows past an impermeable flat plate as shown in the figure given below, with an uniform inlet profile of u is equal to u naught and a cubic polynomial exit profile u is equal to u naught multiplied by 3 eta minus eta cube by 2, where eta is y by delta. Okay, where delta is the thickness of this fluid film over the flat plate. Okay, so assume a width w perpendicular to the plane of the figure and the fluid having a density rho. What is the mass flow rate out of the control volume across the section BC? Okay. So again we are asked to find the mass flow rate. So the simple consideration will be the application of the conservation of mass. Okay, but I think it's much more simpler than that, because they've distinctly told you that you need to find the mass flow rate only out of this surface BC. Okay, so that will basically be a surface of this form, because they mentioned that it has a depth of W across the or perpendicular to the plane of the paper. Okay, so it will only then the mass flow rate out of BC will be m dot BC would be equal to rho U or let me just write it. It will be m dot BC would be equal to the integral of rho U dA from 0 to delta. Okay. So there's the mass flow rate out of the surface BC. And why the integral? Because the velocity profile is changing from 0 to U naught along the perpendicular axis on the axis perpendicular to the flat surface of the plate. Okay, so once you do this integral, such as substitute the value of U here, which would be, if you write it, it will basically be rho U is, if I go back, okay, U naught y E3, it is, if I take 2 also out of 2 common, then we're only left with 3 y by del minus y by delta q W dy. The area would be, elemental area would be W into dy, right? Just perform this integral. So once you do that and put the integration limits, you will get that the mass flux out of BC is equal to 5 by 8 rho U naught W delta. So the correct option, you can just look to the integral, go to the integral once, but it's a very simple integration, so you can pause and check in the video. So once you do that, you will get the correct option to be option A. Okay. So next question is again in the previous problem, so we are discussing the same problem now. What is the volumetric flow rate across the top surface AB of the control volume? Okay. So now here an interesting way to solve this problem is that, so you may ask that here the velocity profile is uniform, so you can just do U naught into W delta as the net volume flow rate. Here we have done the integration to find the mass flow rate, mass flux. Okay, but here you have not given any velocity profile. Moreover, how to find the mass flux out of this surface AB. Okay, so now it's a good time to look back to the question again. So they've told us that the flow moves past an impermeable flat plate. So it basically means that there is no mass flux through this bottom surface. Okay, it is impermeable. Okay, since it is impermeable, I'm sorry. Since it is impermeable, so the mass enters the fluid. This enters this chosen control volume from AD and leaves through AB and BC. Since we know both AD and BC, so from the conservation of mass, we can tell that m dot AD or mass flux through AD would be equal to the sum of mass flux through AB and mass flux through BC, right? So if we need to find m dot AB, we just need to subtract m dot BC from m dot AD. That is m dot, let me just write it, m dot AB would be equal to m dot AD minus m dot BC. Okay. So once you do that, since you know both the expressions, because we already know m dot BC and m dot AD would basically be rho into U naught W delta. Okay, so once you know that, you can find m dot AB is equal to 3 by 8 rho u naught w delta. Okay, so the correct option, you can just go to check the calculation once. So the correct answer in this case would be option number B. Okay. Okay. So okay. So now, as I mentioned, let me just go back to the given problem again. So this problem in itself can again be in a problem that apply that where we need to apply in the conservation of linear momentum. Okay, so in this case they are just asking the mass flux out of the surface AB. Okay, so that was a tricky part, so that we did by applying the mass conservation. But say now, since a fluid moves over a part of an impermeable flat plate, or even a flat plate in that regard, and because our fluid has a certain viscosity, this fluid will impart a certain drag force over the plate, right? Apply the drag force over the plate. And once we are in a regime of questions that deal with the finding of net forces on a particular geometry and flat plate in this regard, we then need to use the conservation of linear momentum to find the net drag force that acts on the plate. Okay, so you will see in the next week that certain similar kind of problems would be asked, and you will be asked to find the net drag force that acts on the flat plate. Okay, on the flat plate, and to do that you need to apply the mass conservation as well as the momentum conservation in the respective manner to find the net drag force that acts on the body. Okay, so you will eventually see how we do that, but I'm just saying same problem, but if different parameters are asked or discussed, we need to apply the particular conservation laws. Okay, so to find a force, we need to find the conservation of we need to apply the conservation of linear momentum. Okay, so so now we have this question. Okay, so I guess this is the last or second last question, if I'm not wrong. No, it is the third last question. We have one more question, two more questions to go. That's fine. Okay. 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 So let's go to the question. So we have that water assumed incompressible flows steadily through a round pipe as shown in the figure given below. The entrance velocity is constant, is u equal to u naught, and the exit velocity profile approximates turbulent flow, u is equal to u max 1 minus r by capital R to the power 1 by 7 power law. What is the ratio of u naught by u max? Okay, again I would say it's a very simple question. They're asking us to find the ratio between the initial velocity profile u naught and the u max that is given in the velocity profile for the exit. Okay, so in order to do that, and since the flow is steady, so we can directly apply the conservation of mass, that is net mass. Since the flow is steady, so the first local derivative or partial derivative part with time would be 0. So we'll only be left with the net mass flux term. Okay, the net mass flux out of the control volume would be equal to 0. That would basically mean that the net mass flux in would be equal to net mass flux out. So we just need to do the balance between the incoming mass flux and the outgoing mass flux. Okay, so once you do that, you will be able to find the relationship between u naught and u max. So let us just go to how we did that. So diagram we have discussed. So as I told you, this is just the balance between the two mass fluxes in and out of the control volume. Okay, since it's a pipe, so we know the area that we are dealing with. Okay, so we would have rho Vr dot n cap dA at inlet is equal to rho Vr dot n cap dA at the outlet. So since the velocity profile is uniform at the inlet, we will have the net mass flux is equal to rho u naught into pi r square. Okay, and at the outlet we will have rho, just substitute the value of the velocity profile here, that is u max 1 minus r by r to the power 1 by 7 into the elemental area. For the index of cylinder it will be 2 pi r dr. Okay, how we reach 2 pi dr? Again, you can just go through the similar problems that we have regarding pipe flows in any standard fluid mechanics book. So you will see that. So it's fine. Okay, you can just, it's a good practice to go to see how the elemental areas are taken for a particular coordinate system. And since in this case we are dealing with a cylindrical coordinate system, the elemental area would be 2 pi r dr. Okay, so once you equate that, we would have rho u naught pi r square will be equal to rho u max 2 pi. We just take all the constants out of the integration, multiplied by the integration of 1 minus small r by capital R to the power 1 by 7 r dr integrated from 0 to capital R. Okay, so this integration is again very simple. Just do a variable transformation. Let us take 1 minus r by r as t. Then for r equal to 0, t equal to 1, and for r equal to r, we will have t equal to 0. Okay, and then dr would be equal to minus r dt, and since 1 minus r by r is equal to t, then r would be equal to 1 minus t into r. So if you just substitute this expressions in this integral, you can write this integral as only this particular part. Okay, this integral as minus integration from 1 to 0 t to the power 1 by 7 1 minus t multiplied by r square dt. Okay, it's just the substitution of these expressions in this integral. Okay, in this integral. Okay, so just carry out the integration. You will find that this integration values to r square into 49 by 120. Then if you substitute this value of integration in back to this equation, you will get that rho u naught pi r square is equal to rho u max 2 pi into r square multiplied by 49 by 120. Then rho is cancelled, pi is cancelled, r square is cancelled. So you will get u naught by u max is equal to 49 by 60. Okay, so let's go to the next question. So the correct option would be an option number C. Okay, so now let us go to the next question. A cylindrical container in the figure given below is 20 centimeter in diameter. Okay, so D is 20 centimeter. Has a conical contraction at the bottom with an exit hole of 3 centimeter in diameter. Okay, the tank contains fresh water at standard sea level conditions that has a relative density of 0.98, and if the water surface is falling at a nearly steady rate of dH by dt is equal to minus 0.072 meter per second, what is the average velocity out of the bottom exit? Okay, so it's again a simple application of conservation of mass, right? So the net mass flux in would be equal to 0, so it will just be balance between the unsteady term and the net mass flux out. Okay, and once you do that balance, you will get that these are all the given parameters. Okay, so rho C water, since it has a relative specific gravity of 0.98, then the density of the sea water would be 980 kg per meter cube. Okay, just multiplied by 1000. Okay, just to recall, relative gravity for a given fluid is, if a fluid or liquid is taken with respect to the density of water. So 0.98 times the density of water, it is what it means. Okay, so the density of the sea water would be 980 kg per meter cube. Okay, and dH by dt is given to be minus 0.072 meter per second. Okay, so once you apply the mass conservation, as I told you, mass in net mass flux inside the control volume would be equal to 0, so it will be equal to 0. So this mass conservation will only be the balance between the unsteady term and the net mass flux out. Okay, so we will have, now just take the terms that do not vary with time out of this time derivative. So we will have pi rho into pi by 4 d square into ds by dt is equal to minus rho into pi by 4 d square into v. Okay, now if we just rearrange the terms, we will get that v is equal to minus ds by dt into d square by small d square. Since we already know ds by dt is equal to minus 0.072, so the minus and minus sign will get cancelled out. So we will only left with v is equal to 0.072 into 20 by 3 whole square. Okay, just the ratio of the diameters. Then we will get that v is equal to 3.2 meter per second, the velocity of the fluid out of the hole at the bottom of the tank. So if we check the options, we will get that v is equal to 3 by 2 meter per second. So the correct option is option D. Okay. So the final question in our hand is a conceptual question once again. So the question is, consider the following statements. Okay. The Reynolds transport theorem is valid for both solids and fluids. Yeah, that's correct, because it's just nobody has told that this equation is for solid or fluid. Okay, they have not mentioned this at all in the while we are deriving or transforming the equations using RTT. Okay, so there is no specification for that. So this is valid for both solids and fluids. Okay, so consequently, then the second statement, that is Reynolds transport theorem is valid only for fluid, becomes wrong. So this is correct, this is wrong. Okay, Reynolds transport theorem RTT for the conservation of linear momentum makes use of the Newton's second law of motion. Yes, of course, because the net rate of change of linear momentum would be equal to net force applied on the control volume. We take that approximation, and that's why this statement is also correct. The given form of RTT is valid for non-deformable control volume. We saw that for non-deformable control volume, we can take the time derivative in the first term inside the volume integral. So this statement is again correct. So the question they have asked is that, which among the following statements given above are true? So we can see that since only 2 is incorrect, so the correct option is option number B, where 1, 3 and 4 are correct. Okay. So again, I feel that's all for today for this session from my side. This week's session, I think it was much more simpler because it's a very fundamental level type of session dealing with the application of Reynolds transport theorem and its discussions of how they are applied, how to choose the control volume, and how to approach fluid mechanics problems in the perspective of conservation laws now. Okay, so in the next week we will be basically dealing with the conservation of linear momentum and how we apply the canonical form of the Reynolds transport theorem to obtain the conservation of linear momentum, and how we apply that in the a given problem. Okay, so I will just suggest that you go through the lectures if possible again and again, so you are well versed with the conservation of mass. Okay, and how to use RTT for applying the conservation of mass. Okay, so that's very important. So I will guess that's all for today from my side, and let's meet all of you in next week, where we will be discussing the conservation of linear momentum using the Reynolds transport theorem. Okay, so thank you and have a good night.